Today we're going to do examples 3 and 4 out of section 2.4. So yesterday we talked about factoring kind of in the old-fashioned way. We talked about these two new patterns, this sum of two cubes and difference of two cubes. And today we're going to talk about grouping and a couple other tricks. So our goal here is to factor these as much as we can. So factoring by grouping comes in handy. Unlike in chapter 1 where we had to multiply and then split, this time we're already kind of in groups here. We're going to consider these first two and these second two. So when you have four terms like this, you can kind of key in that you're going to do factor by grouping. So from the first two terms, I can pull out an x squared, which would leave me with an x minus 3. From the second two terms, I can pull out a negative 16, which would leave me with an x minus 3. Notice again, just like in chapter 1, these now match. So our factors are x squared minus 16 times x minus 3. Now it's tempting to want to be done, but one of the things you're going to look for here is if you have a square term inside of a parenthesis, you're probably not done. Anything higher than a second power, you need to double check and see if you can do anything else. And in this case, this is a difference of squares, which is that pattern where it'll be a squared minus b squared factors to a plus b and a minus b. So this would factor as x plus 4 times x minus 4. And then we still have this third factor, x minus 3. If you're unclear of where this x plus 4, x minus 4 came from, you can review your difference of squares, but remember that's in the form a squared minus b squared, which factors as a plus b and a minus b, so really all you're doing is you're naming an a and a b. I don't have any more powers, so now I know that this is completely factored. Let's look at another one. Part B here, we have 27x to the third plus 45x squared minus 3x minus 5. Again, there's four terms here, so we should think factor by grouping. We group these first two and then the second two. From the first two, I can pull out a 9x squared. You want to pull out the biggest thing that you can. That would leave me with a 3x plus 5. Here I can just pull out a negative 1, which would leave me with a 3x plus 5. So I have a repeat. That's my first factor. Could be my second factor too, I guess. And then what's left is 9x squared minus 1. Now be careful, this is again a difference of squares. So be on the lookout for those. You can recognize those if this whole thing is a perfect square and that whole thing is a perfect square. So my a here would be 3x and my b would be 1. So this will factor as 3x plus 5. And then it would be 3x plus 1 and 3x minus 1. I don't have any more powers, so this is the final answer. And again, if you need to review those difference of squares, let me know. I can point you to some other resources, or you can review from chapter 1. Alright, so that's factoring by grouping, which is actually the easier part of what we're doing today. If you look at example 4, this is more of a dealer's choice of what we're going to do here. So we want to factor as much as we can, and you're going to find that we're going to be left with powers bigger than 2, and sometimes we can go on and sometimes we can't. So let's look at this first one. This is actually a difference of squares, believe it or not, because we can take the square of both parts, square root I should say, and we can get a whole part out of it. So here my a is actually going to be 4x squared, and my b will be 9. So this will factor as 4x squared plus 9 and 4x squared minus 9. Alright, now it's tempting to want to be done, but whenever you have a square inside a parenthesis, you need to double check and see if you can do anything. This we can't do anything to, but actually this part is another difference of squares. So you're going to need to get really good at recognizing those difference of squares, because once you know the pattern, it's really easy to factor those. So the 4x squared plus 9 we can't do anything with, but this one, now my a would be 2x, and my b would be 3. So this second part will factor as 2x plus 3 and 2x minus 3. Now there's no squares in those two last parentheses, and even though there's a square in the first, we can't factor in this anymore, so this is actually our final answer here. Part B, something similar is going to happen here, but before that can happen, the square root of 10, not a perfect square. So let's go ahead and factor out 10 first, so that we're just left with x to the 4th minus 1. Now, this is a difference of squares. And we can factor it where a is equal to x squared and b is equal to 1. So this will factor as 10 times x squared plus 1, x squared minus 1. Now it's tempting to want to be done, but we have to double check here. This one, there's nothing else we can do to it. But this last one is, again, a difference of squares. You can have multiple difference of squares happening here. So we have to factor this one more time. This time, my a will be x, and my b is still 1. So this would factor as 10 times x squared plus 1 times x plus 1, x minus 1. And now it's completely factored. So you can see these can go on a little bit. They're going to require more than one step. Part C here, thinking back to our first example where we try and factor out the biggest thing we can from the whole thing, I can see that I can divide out a 2x squared from this whole thing. So I'm left with x to the 6th plus 5x to the 3rd plus, and then this would be plus 6. Okay, now we're going to use another factor by grouping, but after we do this example, you should notice a pattern that you could follow through with this. So what I want to do is I want to split this middle term. I want to split it into something that I can factor out because I want 4 terms so that I can do factor by grouping. So this 2x squared, and he's just along for the ride. I have x squared. I'm going to split this into plus 2x to the 3rd plus 3x to the 3rd plus 6. By splitting this, now I have 4 terms here where I can group the first 2 and the second 2. So I have 2x squared. From the first 2, I can pull out an x to the 3rd, and I'm left with x to the 3rd plus 2. From this second 2, I can pull out a plus 3, and I'm left with x to the 3rd plus 6. Not plus 6, I'm sorry, plus 2. So this will factor, if you remember your factor by grouping, this is my repeated part, so I have 2x squared, I have x to the 3rd plus 2, and then my last factor is this x to the 3rd plus 3. These powers are bigger than 2, or bigger than 1 even, so we need to double check and make sure there's nothing else we can do. Remember from yesterday we did talk about the sum of cubes, where if this first part is a perfect cube and the second part is a perfect cube, we can use that pattern. Fortunately for us in this one, even though this part is a perfect cube, that's not a perfect cube, that's not a perfect cube. So this is actually our final answer, and it's as factored as we can do it. Part D, we're going to do the same thing here. Let's start though by factoring out a 4x squared. And then we're just working with an x to the 4th minus 5x squared, and then it'd be plus 6. Alright, so again we can group these. We can split this into 4x squared, and then this can become x to the 4th, and then how about we do minus 2x squared minus 3x squared plus 6. So now I have 4 terms, so I can group them. So we'll have 4x squared. From the first 2, I can pull out another x squared, and I'm left with x squared minus 2. From the second one, I can pull out a -3, which would leave me with x squared minus 2. Makes that positive 6 and -2. I now have my repeated factor. So you'll have the 4x squared times x squared minus 2 times x squared minus 3. Again, double check and make sure that these aren't differences of cubes. In this case, that's not a perfect square. That's not a perfect square. So this is fully factored. All right, part E. Let's pull out a 3x squared to start. If you remember from yesterday, I said most of the time it's this first number and the last variable. Not always. It will be the last variable, but sometimes that first number is not going to work. So when we pull out 3x squared, we're left with x to the 10 plus 54 divided by 3, I think it's 18. Yep. 18x to the 5th plus 17. All right, so again, we can do factor by grouping, but really quick, I want to draw your attention to a pattern that ends up happening here. If you notice this first one, you don't have to write this part, but notice we had an x, so this was a 6, 3, and then no power. And if you think about it, if this hadn't had a 6, if this had just been a square, and if that had just been an x, this would have been just factored like the old-fashioned way, where 2 times 3 is 6, but 2 plus 3 is 5. So the trick that you can do, and you don't have to do this, you can keep factoring by grouping, but you can think that this is going to factor, we'll have the 3x squared, it's going to factor as an x to the 5th, another x to the 5th, and then you just have to figure out what you're plus or minusing. And that comes from this 17, what multiplies to 17, but adds to 18. So in this case, 1 and 17. So you just do plus 1 plus 17. This way works as well, if you can remember that pattern. This is just us using the pattern we've noticed. There's nothing particularly mathy about it. And we double check to make sure that we can't factor these further. We have no idea how to factor something with the 5th power, so this is fully factored. So you can see that pattern lasted for this example as well. If you just think of this as a square and that has no power at all, then you are multiplying to 6 but adding to -5, and in that case -2, so I should say -2 and -3 would get you there. So that way works as well. Basically you just think this is half of whatever that power was in the end, and then your two factors. But like I said, you can still use factor by grouping. So if you have any questions about this, let me know, and I can try and clear those up for you.